So this unit is a little different because we're going to be talking about mostly, we're going to do a little bit of algebra at the end, counting, which is related to probability in math, okay? So like, let's say, for example, you guys are familiar with Lotto 649? Okay, it's a lottery in Canada that what you do is you, out of 49 numbers, you choose 6, and if you get all 6 right, you win $5 million. Okay, so something that we would want to know is what's the probability of actually winning 649? Well, we would need to count the ways that you could possibly win, and there are a lot of them, which means the probability of winning $5 million is pretty low. Okay, but that's just one example of where we use counting. And one type of counting involves something called permutations. Okay, so like I just said, counting methods are used to determine the members of a specific set as well as the number of outcomes. Of some of that. So as an example, a restaurant has the following options for pizza. We'll keep it fairly simple. Meat, they only have pepperoni and bacon, and vegetables, they only have onions, green peppers, and mushrooms. And the lunch special requires you to order 1 meat and 1 vegetable. How many possible different types of pizzas can you make? Well, there's a couple of ways we can look at this. And one, if you're in AP Stats, you will be familiar with this, is a tree diagram, but it's a little different, okay? So you choose your meat. So you're either going to have pepperoni or bacon. 2 possible choices for the meat. Let's say you choose pepperoni. How many possible choices are there for the vegetables? 3. Onions, green peppers, and mushrooms. If you decide to choose the bacon for the meat, again, there are 3 choices for the vegetables. Onions, green peppers, and mushrooms. So how many possible pizzas can you make? 6. There's 6 possibilities. Tree diagrams aren't very efficient, okay? Especially if the numbers are larger. So we want to find a different way to do it, and something called the fundamental counting principle is a way we can do it without having to do all this drawing. So what we want to do is say, okay, a pizza is made up of a meat and a vegetable. And what I'm going to do is I'm going to put the number in for the possible choices for meat. How many possible choices are there? 2. How many possible choices are there for the vegetables? 3. To find the possible to find the number of different types of pizza, I multiply those together. And notice again, I get 6, and we can see that's much more efficient. And we're going to be relying more on this than we are going to worry about these. Because really, with these, we would really only do those if we're dealing with small numbers. But when the numbers get larger, you want to use what's called the fundamental counting principle. which basically says if you can choose one item in a number of ways and a second item in B number of ways, then the two items can be selected together in A times B ways. And we can even apply that to a third item, a fourth item, a fifth item, a sixth item, which we'll see shortly. So as an example, while backpacking in Europe, Herman bought 4 shirts, 5 pairs of shorts, 3 pairs of shoes. How many different outfits are possible? Right. Because we need a position for the shirts, we need a position for the shoes, and we need a position, for the shorts and then the shoes. And how many possible shirts? 4. How many possible shorts? 5. How many possible pairs of shoes? 3. And to find all 3 items, we multiply. And there are 60 possible combinations. 60 possible arrangements. Okay. Another example, and we talked a little bit about this yesterday. How many 3-digit numbers can you make using the digits 1 to 7 without repetition? Meaning digits cannot be repeated. Well, in this, we've got a 3-digit number, so there's 3 positions. And let's start with the first position. How many possible digits could I put in here? 7. Now I can't repeat, so I've used one up. How many possible ones are left here? 6, and I've used the second one up, then 5. Multiply 210. Now, sometimes there may be restrictions on what you're asked. And you always fill in the restrictions first. This will become clearer when I do this next example. How many of the above 3-digit numbers are even? 12. Let's look at it this way. I don't want to start with this position. The restriction is they have to be even, which means the last number has to be even, right? Out of all these choices, how many of these are even? 3. So I have to put in that first. Now I've used the digit up, I can go back here. How many is there? No, I can use any digit now, but I've already used one. 6. I've used another one. 5. And multiply. So we get 9. How many are odd? Again, that's a restriction, which means I have to fill in how many possibilities for the last position of the 3-digit number. This time there's 4, because there's 4 odd numbers to choose from. And then there's 6 digits left, because I can put any digit I want in here. And now there's 5 digits left for the second. And we get 120. Which makes sense because here's the number of odds, here's the number of evens, here's the total. These two have to add to this. Last question in this example, how many are greater than 300? So that's a restriction. But what position does that affect? The first one, right? Because it has to be greater than 300. So how many possible digits could I use here?
3, 4, 4, 5, 6, or 7.
Can't you use 3?
It wouldn't be bigger than
Sure it will.
3, 4, 5, 6.
Right. You could use 3, 4, 5, 6, or 7. So there are 5 possible choices for the first position. Now you've used one of those up, and the other numbers can come back into play now. The other digits come back into play. We've used a 3, 4, 5, 6, 7, one of those. So 4 of those are left, and 1 and 2 are possibilities, right? So that means there's 6. And then here, 5. Because there's there were 6 possibilities here. I used one up, which means there's 5. So there's 150 numbers. Okay. Depending on the question, we can use a certain type of notation to make things a little easier on us. So as this example, for example, how many 4-letter different words can be used using the letters A, B, C, D? And I put words in quotation because A, B, C, D is a word, even though it doesn't make sense, it's an actual word. So there's 4 positions. How many possible, there's no restrictions. How many possible letters could I put here? Then, and 4 times 3 times 2 times 1 gives us 24 words. When the multiplication looks like this, we start at some number and we keep multiplying 1 less until we get all the way to 1. That's actually a special type of notation we can use. We take the number, in this case it's 4, and we put an exclamation mark after it. That means factorial. It's very straightforward. Whenever you have a number followed by an exclamation mark, you start with that number and you multiply all the way down to 1. So 3 factorial is 3 times 2 times 1. 8 factorial is 8 times 7 times 6 times 5 all the way down to 1. That's all that means. Okay? And you do have this on your calculator. So mathematically, whenever you are asked to take some number and do the factorial on it, you take that number, you multiply by 1 less, then you multiply by 2 less, and you keep multiplying until you get all the way down to 1. And this 0 factorial is actually equal to 1. Okay? Now, we can actually play around with factorials a little bit. Okay? So for example, if I said 9 factorial, yes, that means 9 times 8 times 7 times 6 times 5 all the way down to 1. But it also means this. Take 9 and then times it by 8 factorial. We'll see why we do that in a second. Okay, or I could do 9 times 8 times 7, and then if I want to stop there, I'll put factorial. And I can keep doing that. If I use n, I could say n factorial is equal to n times n minus 1, and then I can stop there and put a factorial. Yeah. No. It always stops at 1. Good question. Or I could do, okay, I'm going to take that number, I'm going to multiply by 1 less, I'm going to multiply by 2 less, but then I'm going to stop there and put a factorial. And again, etc. And you can only take the factorial of whole numbers, meaning 0 and up. Okay? So 0 factorial is 1, 1 factorial is 1, 2 factorial is 2 times 1, 2, and so forth. So here's how we can use this property. Because we may encounter questions where we have to simplify factorials. And this is how you can do it. An inefficient way would be to go 10 times 7 times 6 times 5 all the way down to 1, divide 9 times 8 times 7 times 6 times 5 all the way down to 1. If we use what I just talked about on the last page, couldn't I represent 10 as this times that? What happens to the 9 factorials? So my answer is 10. So you're able to do that without having to do a whole bunch of multiplication. Okay. So what you do when you encounter questions like this is you take the bigger number and then you start multiplying by 1 less until you get to the smaller factorial. And then you cancel with it. So for example, I wouldn't touch this, but I would start writing this down until I got to 5. So 7 times 6 times 5. Now I want to stop and put a factorial there because I can cancel it with the top. So those cancel, remember it's 1. So we're left with 1 over 42. This one, well, I can start writing the 12 as 12 times 11 times 10 times 9 times 8, and then I'll stop. Because I can cancel it with the 8 factorial on the bottom. But now I'm left with 12 times 11 times 10 times 9 over 4 times 3 times 2 times 1. I mean, I could do some more canceling. I could say, okay, I'm going to take 12 and 4 and cancel that down to 3. Because 12 over 4 is 3. I could take the 9 over 3 and cancel that down to 3. I could take the 10 and 2, 10 divided 2, and cancel that down to 5, but I'm still left with a rather big multiplication. Okay. So what would this give us? 99 times 5, 495. Sure, yeah, 495. But we would do that canceling technique with ones like that. you would see ones like this more than you would see something like this. Now you may see ones like this, and we'll see this towards the end. Again, take the bigger one and start writing down until you hit the smaller one. So out of these two, n and n minus 2, which one's bigger? N, right? Because this is 2 less. So take the n and start writing, well, okay, 1 less, and then multiply by 2 less. That matches the denominator. Stop and put a factorial. Because now I can cancel that with the bottom. And I'm left with n times n minus 1, or n squared minus n. Similarly, which one's bigger? N minus 4. So take the n minus 4 and start writing 1 less, n minus 5. Well, I can stop there because that matches the denominator, which allows me to cancel. So I'm left with n minus 4. We're going to see that we use this when we solve permutation equations on the next page. So what we've been doing here, these type of examples, besides the factorial, the problem solving ones, are permutations. Okay? And a permutation is an arrangement of objects in a specific order. So for example, if I was to arrange you 3 in a certain order, I could go Lilia, Ayla, and Anna, or I could go Anna, Ayla, and Lilia. Those are 2 different ones. Okay? When we talk about combinations, those 2 are the same. But we'll talk about that later. Okay? They're arranged in a specific order. So when we permute a set of objects, we are arranging. So as an example, we've got the letters A, E, and T. We want to list the different ways to rearrange them. Well, I mean, if we do it just sort of writing them out, I would go, okay, I could do A, E, and T. I could switch the order of the E and T and get a different arrangement, even though it contains the same letters. No other arrangements that begin with A, so I could go E, A, T. Rearrange the A and T and get ETA. No other arrangements that begin with E's. Let's start ones to begin with T, TAE, and TEA. So we see that there's 6. Okay? Well, we could have found that by the fundamental counting principle. We can also find that using permutations. And this is specific permutation notation. What does this mean? It means take the number at the beginning, take its factorial, and divide by the number at the beginning, subtract the number at the end, its factorial. You will always get this formula. You don't have to remember it. Okay? Certain restrictions, n has to be a whole number, so it has to be greater than or equal to 0, and it has to be greater than or equal to r.
So if I did this kind of notation with this example, I could do this notation, or I could do FCP, the fundamental counting principle, which we've already done. So what I would do is I would say to myself, okay, out of 7 members, how many arrangements of 3 can I make? So in this specific example, out of 7 members, how many ways can I make arrangements of 3? So what we would do, using the formula, 7 factorial over 7 minus 3 factorial, which is 7 factorial times 4 factorial. And using that simplifying that we talked about above, this is the same as 7 times 6 times 5 times 4 factorial over 4 factorial. I stop there because I can cancel those two. And I get 210. We could have used the fundamental counting principle, and in many ways, I would suggest you use the fundamental counting principle because a lot of times it seems easier. Because I would just do this. I would say, okay, there's 3 positions, student council positions. There's 7 ways I could choose the chair. So the chair has been chosen, which means there's 6 left for the next position, secretary. That's been chosen, which means there's 5 left for that. Obviously, it has to work out to the same amount. Okay. So you could use the NPR, or you could use just the fundamental counting principle. Okay. This is a function on your calculator. Okay. So you could do like 7, find that function on your calculator, and then 3, and then equals, and it'll give you 210. Different calculators, it's located in different spots. Wow. How do we solve permutation equations? Well, we have to use the permutation formula. NP2 means take the first one n and factorial over n minus the second number factorial is going to equal 30. I have to solve for n. Well, the first thing I want to do is get rid of the factorial. And we do that like we did on the previous page. Take the bigger one, start writing down until you hit the smaller one, and then put a factorial. What could I do now? And I'm left with n times n minus 1, or n squared minus n equals 30. Got rid of the factorial. It's a much easier equation now. Now what do I do? I'm hearing mumbling.
Move it to the other side of the map.
Okay, you have to factor it because it's quadratic. So n squared minus n minus 30 equals 0. And what do we get? Minus 6, I thought I heard, plus 5. Which means n equals 6 or negative 5. But n always has to be positive, doesn't it? We can't have a negative.
So the only answer is 6. Okay? The last equation. Well, using the formula, the first expression up top with the factorial over the first expression minus the second number factorial equals 72. Well, I can simplify the bottom to n minus 3. Like so. Now remember, we're solving for n, so we want to get rid of the factorial. How do we do that? Okay, take the top and start going down until you hit the expression that's the same as the bottom. Put a factorial. And that allows me to take those out. And I'm left with n minus 1 times n minus 2 equals 72. Well, I'm going to have to multiply this out, bring the 72 over, and then simplify to factor it. So I get n squared minus 2n minus 1n is minus 3n. And then negative 1 times negative 2 is plus 2. Equals 72. N squared, got to bring the 72 over. So that gives me minus 70. I'm ready to factor. What works? Negative 10, positive 7. Which means n equals 10 or negative 7. We can't have a negative. So our answer is just 10. Okay. Equations like these often appear on the provincial. Not every year, but often. Okay. So it's important to know how to do those. But you will see questions on permutations and what we're about to do, combinations later on. Okay. But there's more types of permutations we can do that we'll talk about next time. Okay.